I am Dr. Himamaheswara Rao, Assistant Professor of Physics, Department of Freshman Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Welcome to the lecture series Atomic and Molecular Spectroscopy. Today we are going to discuss the topic quantum states and spectroscopic terms. This is the part 3 of this topic. So here we try to solve some problems related to this topic. So the first problem is calculate the two possible orientations of spin vector S bar with respect to a magnetic field B bar. So in general, for any electron, it could have electron orbital angular momentum and spin angular momentum. So we represent these two momenta in terms of vectors. So that means we represent orbital angular momentum by orbital angular momentum vector L bar, and spin angular momentum by is represented by spin angular momentum vector S bar. So here the problem is to find out possible orientations for the spin angular momentum vector S bar. So in general we represent with reference to the magnetic field B bar. So generally if there is a nucleus, electron revolves around the nucleus in certain orbit. So if we represent the electron spin with a vector S bar, so this is the electron spin angular momentum vector S bar. So it is present in the magnetic field B bar. Let us, the electron is present in the magnetic field B bar, and the direction of magnetic field is along the direction of Z axis. So this is the Z axis and magnetic field is the direction of Z axis. So here the angle made by the spin vector or spin angular momentum vector S bar is theta. And then we also consider spin angular momentum along the Z axis, that is Z component of the, that means component of the spin angular momentum along the Z axis or field direction is Sz. So Sz is the component of spin angular momentum along the Z direction. So in general, the length of or the magnitude of Sz is given by S into, as theta is the angle between Sz and S into cos theta. Here S is the magnitude. So this is also magnitude. In general, Sz is also similar to Lz. It is also a scalar. So theta is the angle between Sz and S bar. So the angle between S bar and Sz can be calculated by the values of, or the magnitudes of Sz and S. So quantum mechanically, these two magnitudes, that means Sz and S are given like this. The magnitude of spin vector is taken as square root of S into S plus 1 h by 2 pi. And the magnitude of Sz is equal to ms into h by 2 pi. Here S is the spin quantum number. S is the spin quantum number, and ms is the spin magnetic quantum number. Okay, and again here the value of s is always 1 by 2 for any single electron. The value, that means spin quantum number, is 1 by 2, and the values of ms for s equal to 1 by 2 should be equal to plus or minus 1 by 2. So it can have two values, 1 by plus 1 by 2 minus 1 by 2. So we can easily calculate s value. Let us see here. S equal to square root of smallest value is 1 by 2 into 1 by 2 plus 1 into h by 2 pi. So that means 1 by 2 into 3 by 2, that is under square root h by 2 pi. So here we can easily simplify this term, square root of 3 by 2 h by 2 pi. And again the magnitude of sz is equal to ms h by 2 pi. So here the ms can have two values, either plus 1 by 2 or minus 1 by 2. So plus or minus 1 by 2 into h by 2 pi. That is the z value. So in order to find out the angle between the vector x bar and sz is cos theta. By finding cos theta, we can calculate the angle between those two. So sz, this is the sz. So plus or minus 1 by 2 h by 2 pi by, and again s, the magnitude of s is square root of 3 by 2 h by 2 pi. Square root 3 by 2 h by 2 pi. So you can simply here cancel these two terms, and after simplifying we can easily reach to the value plus or minus 1 by root 3. 1 by root 3. So this is the cos theta value. So in order to find theta, so theta is equal to cos inverse of 1 by root. Here, here it is again, there should be plus or minus 1. Plus or minus 1 by root 3. That means there are two theta values. One is cos inverse of 1 by root 3, and the second one is cos inverse of minus 1 by root 3. So if we calculate these values, we will obtain 54.7 degrees. The second value 125.3 degrees. So there are two orientations for spin of the electron. One is 54.7 degrees and the second one is 125.3 degrees. That is the angle made with the magnetic field direction. So those two orientations of the spin are represented here in this diagram. So for ms is 1 by 2, for ms value 1 by 2, we are getting the orientation of electron with 54.7 degrees with the z axis. The angle made by the electron for the orientation ms 1 minus 1 by 2 having angle 125.3 degrees with the z axis. Okay, these are SZ values, the component of Z component of spin vector along the Z direction or magnetic field directions. 1 by 2 h by 2 pi, and the other one is minus 1 by 2 h by 2 pi. So the magnitude is also, you can see here, the magnitude of, that means the length of the spin vector, square root 3 by 2 h by 2 pi. This is the magnitude of the spin vector. Okay, so these orientations of spin vector are shown in this diagram. So let us go to the second problem, that is, for an electron orbit with quantum number L equal to 2, state the possible values of the components of angular momentum along a specific direction. In general, the electron orbital orientation will be taken with the reference of magnetic field direction. So in order to represent or describe the electron orbit orientation, we take the magnetic field direction. So here also we should represent direction of, or the possible values of the components of angular momentum into the direction of magnetic field. Here the quantum number is given as 2. Quantum number is 2. So to find out the, with quantum number L equal to 2, state the possible values of the components of angular momentum along a specific direction. So here the orbital, as in the earlier case, if we take the nucleus, center of the nucleus, the direction of magnetic field is in the direction of z-axis, and this is the orbital angular momentum vector L bar. So the component of L bar, orbital angular momentum, that is Lz, is given along the z direction, and if you try to find out or calculate the component of Lz, uh, component of orbital angular momentum vector, that is Lz, we need ml into h by 2 pi. So here ml is the orbital magnetic quantum number. It represents the different orientations, different possible orientations of the orbital angular momentum. So in general, for L equal to 2, ml can have values 2, 1, 0, -1, -2. So ml values will be equal to from L, L-1, L-2, etc. 0, 1, 2, etc. up to uh, if ml L is given, for any L, the ml values will be like this: L, L-1, L-2, so on, 0, 1, 2, up to minus -1, -2, up to -7. So that we have taken the ml values like this. So if you want to find out, calculate the angular momentum. Angular momentum here for single electron, for L equal to 2, here L equal to 2 and S is equal to spin quantum number is 1 by 2. Then here angular momentum means total angular momentum. They are asking total angular momentum. So to find out the total angular momentum, we need to find J values. So that J can be calculated as J equal to L plus or minus S. L plus or minus S. So here for any L, for the single electron, S could have only either plus only 1 by 2. So here L plus or minus 1 by 2. So for L equal to 2, J equal to 2 plus or minus 1 by 2. That means 3 by 2 plus 1 by 2 means 5 by 2, comma 3 by 2. 2 minus 1 by 2 means 3 by 2. So these are the J values. J values. So to find out the total angular momentum component, total angular momentum component, that means okay. So we are finding the total angular momentum component along the Z direction. So for Z direction components, we need mj values. So for J equal to J have two values. For J equal to 5 by 2, then the values of mj can have 5 by 2, 3 by 2, as like here as ml values. Similar to ml values, we can take mj values also. So 5 by 2, 3 by 2, 1 by 2, minus 1 by 2, minus 3 by 2, minus 5 by 2. And for the values, for the J value, 3 by 2, the mj can have values, the second value 3 by 2, 3 by 2, 1 by 2, minus 1 by 2, minus 3 by 2. So on comparing, if we take all possible mj values, we can have these values. And again, if you want to find the Z component of J bar, total angular momentum vector, so that is Jz equal to mj into h by 2 pi. So we can have values, the Z component of total angular momentum can be 5 by 2, or we can write simply we can write 5 by 2 h by 2 pi, comma plus or minus 3 by 2 h by 2 pi, comma plus or minus 1 by 2 h by 2 pi. So these are the different possible values for the components of total angular momentum having electron orbital with value L equal to 2. So these are represented with the direction along the magnetic field. So let us go to third problem. Calculate the possible orientations of the total angular momentum vector j bar corresponding to j equal to 3 by 2 with respect to a magnetic field along the z-axis. Calculate the possible orientations of the total angular momentum vector j bar corresponding to j equal to 3 by 2 with respect to magnetic field along the z-axis. So calculate the possible orientations of the total angular momentum vector j bar corresponding to j equal to 3 by 2 with respect to a magnetic field along the z-axis. So here also the vector j bar, we need to represent the vector j bar, total angular momentum vector j bar with reference to the magnetic field direction, which is in z-axis direction, parallel to the direction of z-axis. So we need to find the angle between b direction and j vector direction to find out the total all orientations of the j bar. So that means for that we also take the z component of the total angular momentum vector, that is jz in the direction of magnetic field, and the component, the magnitude of the component jz is given by the quantum mechanical relation. Quantum mechanical, it is given by the relation jz equal to mj into h by 2 pi, mj into h by 2 pi, and the magnitude of j bar is also given by the magnitude of j bar is also given by the quantum mechanical relation square root of j into j plus 1 h by 2 pi. Here j is the quantum j is the total angular quantum number, total angular momentum quantum number, and mj is the magnetic quantum number corresponding to the total angular quantum number. J is also called inner quantum number. J is also called inner quantum number. So mj is the magnetic quantum number corresponding to the inner quantum number. mj is the magnetic quantum number corresponding to inner quantum number j. So if the j value is given as 3 by 2, the possible mj values, so for j equal to 3 by 2, mj can have 3 by 2, 1 by 2, minus 1 by 2, minus 3 by 2. There are 4 possible values for the mj. So we need to find possible orientations of the total angular momentum vector j bar corresponding to j 3 by 2. So here also we need to find angle. So for that we can calculate, we can take the relation cos theta equal to j z by j, the magnitude of gz and vector j. So jz is given by mj into h by 2 pi. J bar, magnitude of j bar equal to square root of j into j plus 1 h by 2 pi. So after simplifying this, we'll get mj by square root of j into j plus 1. The value of mj changes. There are 4 possible values for mj, but j is equal to 3 by 2. So this is equal to mj by square root of 3 by 2 into 3 by 2 plus 1. So it is also simplified as 3 by 2 into 5 by 2, that is under square root. So we are going to get square root 15 by 2. That means cos theta equal to 2mj by square root 15. Square root 15. So here mj can have values 3 by 2, 1 by 2, minus 1 by 2, minus 3 by 2. So cos theta values can be taken as 3 by mj, 2 by square root 15 is common. So mj values are, these are the mj values, 2 by 15, mj values 3 by 2, 1 value, 2 by square root 15, 2 by square root 15, 1 by 2, 2 by root 15 minus 1 by 2, 2 by root 15 minus 3 by 2. So these are the cos theta values. So we can easily simplify 3 by root 15. This value comes as 1 by root 15 minus 1 by root 15 minus 3 by root 15. We will simplify these values into, so if we calculate this value 3 by square root 15, you will get 0.775, and 1 by root 15 we are obtaining 0.258, and this is minus 0.258. This value minus 0.775. We calculate all these values, and again this is the cos theta value. If we find out the theta value, that means cos inverse of these values. Cos inverse 0.0775, we are getting 39.2 degrees. For cos inverse of 0.775, we are getting 39.2 degrees, and cos inverse of 0.258 is 75 degrees, and minus cos inverse of minus 0.258 means 105 degrees. Cos inverse of minus 0.258 is equal to 105 degrees, and cos inverse of minus 0.775 is 140.80 degrees. 140.80 degrees. So these are the orientations possible for the different orbital angular momenta vectors. So these are also represented in this diagram. So this is for this value we are getting when mj is equal to 1 by 2. So this is the angle made by the z axis made by the this is the angle made by the total angular momentum vector with the z axis. This is the angle made by the total angular momentum vector with the z axis for mj value here. No. So this is the here mj value is 3 by 2. We are taking 3 by 2 mj value. So for mj 3 by 2 we are getting 39.2 degrees. That means for mj 3 by 2 this is the angle. This angle must be 39.2 degree. And for mj value 1 by 2 we are getting 75 degrees. The total orbital angular momentum vector is making 75 degrees for mj value 1 by 2. So for mj value 1 by 2, the angle made by the j vector with z axis is 75 degrees. And then for minus 1 by 2, we are getting 105 degrees. So this is 105 degrees for mj value minus 1 by 2. So for 140 degrees, that is we are obtaining at mj value minus 3 by 2. So this is the angle 140.80 degrees. So this we are getting when mj is equal to minus 3 by 2. So these are the all possible orientations of total orbital angular momentum vectors with z axis when j equal to 3 by 2. Orbital total angular momentum vector j equal to 3 by 2. So these are all possible orientations of j vector. So now let us go to the fourth problem. So determine the possible terms of a one electron atom corresponding to n equal to 3 and compute the angle between L and S vectors for the term 2d 5 by 2. So this is the one of the term when n equal to 3. So let us find possible terms for single electron atom. So when the electron is revolving in the third orbit, n equal to 3 is third orbit. So when the electron is in the third orbit, n equal to 3. So for n equal to 3, the possible L values are 210. So here we need to find the angle between L and S. So L and S, when L is in this direction and S maybe in this direction. So the angle between L and S can be calculated from. Okay, now let us see the fourth problem. Determine the possible terms of a one electron atom corresponding to n equal to 3 and compute the angle between L bar and S bar vectors for the term 2D 5 by 2. So here n equal to 3. That means the electron, that is also single electron uh, is present in the atom, and that electron is revolving in the third orbit. That means n equal to 3. So for n equal to 3, you can have L values only 210, and the S value, as there is only single electron, the spin quantum number S will be 1 by 2. So the total angular momentum quantum number J can be calculated by L plus or minus S. So for L equal to 2, the J value can be calculated as L plus or minus S. So for L equal to 2, 2 plus or minus 1 by 2. So that means we are getting 2 plus 1 by 2 means 5 by 2, or 2 minus 1 by 2 means 3 by 2. And for L equal to 1, we can have 3 different L values for the electron which is orbiting in the third orbit, n equal to 3. So for L equal to 1, the total angular momentum quantum number J can have values 1 plus or minus 1 by 2. That means 1 plus 1 by 2 means 3 by 2, or 1 minus 1 by 2 means 1 by 2. And for L equal to 0, that J value can have 0 plus or minus 1 by 2. Here in general, J cannot have negative value, so we can have only one value, 1 by 2. The J value is equal to 1 by 2. So here the spectral terms can be written as, for L equal to 2, J, and we also need multiplicity. Generally we write some L value here. Here multiplicity, we need to write J value of particular quantum state, that is called spectral term. This notation is called spectral term. So here for L equal to 2, the spectral term L is for L equal to 2, the designation is D. Let us go from L equal to 0. For L equal to 0, the spectral term is S, and multiplicity, here we need to calculate multiplicity also, as S is equal to 1 by 2, we can have multiplicity 2s plus 1 value 2 into 1 by 2 plus 1, that means 1 plus 1 2. So the multiplicity is 2. So this is the multiplicity. So the multiplicity for this case is 2. So here we need to indicate multiplicity, left superscript, and write down write subscript. We should write J value. So L equal to 0, the J value is 1 by 2. So we need to write like this. So this is the one quantum state of the electron having n equal to 3 value. And next one, if L equal to 1, then J values can be either 1 by 2 or 3 by 2. Then the electron state can be, so for L equal to 1, the designation for L equal to 1 is P. Multiplicity is in this case also as it is single electron 2p. So J values can be either 1 by 2 or 3 by 2. So 2p 1 by 2 is one state of the electron, and 2p 3 by 2 is another state of the electron in the orbit n equal to 3. And for L equal to 2, if L value is 2, then the designation is D, multiplicity is 2, and the J values, possible J values are 3 by 2 and 5 by 2. So 2D, 3 by 2, 2D, 5 by 2. These two are possible spectral terms for L equal to 2. So whenever the electron is orbiting with n equal to 3, principal quantum number n equal to 3, there are 3 possible L values, and these are the possible J values. So according to N, L, J, we can represent different state of electrons like this. So there are 1, 2, 3, 4, 5 states, 5 quantum states are possible for the electron, single electron. Okay, so like this we can solve uh, quantum states for the electron with reference to the principal quantum number. So now one more problem here, we need to find or compute the angle between L bar and S bar vectors for the term 2D pi by 2. So in general for this, we also know that even we can determine the angle between L and S whenever we take total angular momentum vector J bar. So this vector can be represented as vector summation of L bar and S bar, and whenever we square on both sides to this equation, so we will get magnitude of J bar. So this is equal to L bar plus S bar whole square. So this equation, on expanding this, we are getting L square plus S square plus 2 into L bar dot S bar, or we can write 2LS cos of L comma L bar comma S bar. So that means cos of angle between the vectors L bar and S bar. So this is the magnitude J square. So bring these two terms to the left side. We can write this expression as 2LS cos of L comma S equal to J square minus L square minus S square, or otherwise we can represent this equation as cos of L comma S bar equal to J square minus L square minus S square by 2 into LS. So all the values, all the variables here are magnitudes of those particular vectors. So here J square is equal to J into J plus 1, because we know that the magnitude of J bar equal to square root of J into J plus 1 into H by 2 pi. So L H by 2 pi, here we need to write H by 2 pi. Let us write. Otherwise we can easily cancel H by 2 pi in each and every term in the denominator and and both up and down. So remove this to simplify for our convenience. So j into j plus 1 minus L into L plus 1 minus S into S plus 1 by 2 into square root of L into L plus 1 and square root of S into S plus 1. Here the j value for the we need to calculate the angle between L and S for the term 2d phi by 2. So in this term the L value L is here, this is the L. D means the L value for D is 2 and multiplicity here multiplicity is 2, that means S is equal to 1 by 2 and the J value is 5 by 2. J value is 5 by 2. So we can easily calculate all these parameters on substituting these values. So cos L comma S bar equal to J into J plus 1. So 5 by 2 into 5 by 2 plus 1 means 7 by 2. Okay. And again minus L into L plus 1 means 2 into 3 minus S into S plus 1 1 by 2 into 3 by 2 by 2 into square root of L into L plus 1 means 2 into 3 and square root of S into S plus 1 means 1 by 2 into 3 by 2. So if we calculate this value 35 by 4 minus 6 minus 3 by 4 by 2 into root 6 into root 3 by 4. Maybe we can cancel these two terms if it comes outside, and here if we simplify this one 35 by 4 minus 3 by 4 means 32 by 4. 32 by 4 means 8 minus 6 finally by square root of 18. You can write this as 18. So 2 by root 18. 9 into inside 18. 18 means 9 into 2. 9 into 2. So 3 square root of 2. So this is equal to square root of 2 by 3. So cos of L comma S equal to square root of 2 by 3. So the angle between, let us write here, the angle between, that means theta angle between L and S is given by cos inverse of 2 by square root of 2 by 3. The value of root of 2 by 3 can be calculated as, okay, the value of square root 2 by 3 is 0.4713. So this value is obtained as 61.9 degrees. So the angle between L and S for the spectral term, that means when the electron is in the energy level 2d by 5 by 2. 2d 5 by 2 is 61.9 degrees. So you can calculate the angle between orbital angular momentum vector and spin angular momentum vector whenever the spectral term is known. So these are the references. Thank you all.